Thanks, Christoph. Thanks. Of course, first of all, I'd like to thank the organizer for having me here to speak on this work. And everything I say is a joint work with Emmanuel Grenier, who's also here. All right, so maybe first one has to look at the settings of what we're doing. We say the implicit limit. Let's say the implicit limit. So the equations we're looking at is the incompressible Navier-Stokes equations, which you already seen. But okay, let's write it again. Navier-Stokes. Okay. Equations. Yeah. If you have any questions, please feel free to stop me and ask. Okay. So first of all, okay, the equation. Let me remember the equations. All right. Huh? I'm sorry. Okay. Oh, it's okay. Okay. So the equations. Let's see. So this is the equations for incompressible Navier-Stokes. Right. So you have equation for U, and then you have the divergence free conditions, and you have initial terms equals U0, and you have the boundary conditions. Okay. So the equations is based on a domain omega, and let's say the omega for now is in RD. Okay. All right. And in this problem, of course, for sufficiently smooth, this is well known, for sufficiently smooth data, U0, you get, then of course we have sufficiently smooth solutions. So that's solutions. U new, let me call it U new, at least in a very short time, let's say, okay, for some t positive. So that's the exactly equations that I'm doing in these problems. The objective of this, is the asymptotic behavior of U new as nu very, very small. Okay, this is the objective of these problems. Look at the incompressible Navier-Stokes equations on the domain with the boundary, and you wanted to understand asymptotic behavior of these solutions. And by the way, the time existence, it's also independent of nu, right? Because this is also true for Euler. So of course, you can take it small so that it's independent of nu. Okay, independent of nu. And what we call the implicit limit. I don't know how to write implicit limit. Implicit limit. That's it. Yeah, implicit limit problem. Implicit limit problem is that okay, for let's say smooth U0. I'm not very precise in the smoothness of U0, but that's okay. Then there's a time t positive, so that you have U nu minus U Euler in L2 in X, supremum in time, go to 0. Okay. go to 0 as nu go to 0. So this is the implicit limit. This is what you like to.
What you take at the boundary condition for the Euler?
Exactly. Yeah. So here, that's a great question. Here at nu equals 0, so we get Euler. So UE is supposed to be solution for Euler. In fact, this at least the problem we wanted to prove is as soon as the solution of Euler exists. But okay, so the Euler solutions. Euler equations. Okay, Euler equations is looking like this. U Euler plus U, at least that's what you expect us to see. Okay, and then you still have the same divergence-free conditions. It's okay. I mean, you're allowed to take the same initial datum. That's fine. The same initial datum. And the Euler equations, you only need the normal conditions, right? I mean, sorry. The U dot n. So the n is the normal directions to the boundary equals 0. So of course you realize right away that there's a mismatch of the boundary conditions, but all right, because this is summer school, so I assume that there are many students. So if I boast a problem, so let's to think about it a little bit. So maybe naively, you wanted to solve this. Naively, so is it clear what I'm saying? So you get the Navier-Stokes equations with a small viscosity nu, and of course nu is supposed to be positive. I didn't say anywhere, but okay, nu is supposed to be positive and very small. At nu equals at.
What you wrote is a theorem or is what you...
No, the problems. I said problem, the implicit limit problem, or at least the dream you wanted to prove. Okay. Let's say.
It's not a theorem.
Not a theorem. Not yet. But because we have so many students, let's say naively you want naively. So naively, if you write U nu equal U minus UE, okay, then of course the difference, you wanted to prove that the difference in L2 converging to 0, then the difference of, all right, so I'm going to do very quick because difference like that, I think you trust me with that, B equal nu plus of U nu, okay? You still have the divergence-free conditions, V equals 0. However, of course, so V initial conditions to it to be 0. I don't mind at all. But the boundary conditions, I wanted to save some space. The boundary conditions, of course, is V dot n equals 0, but V tau meaning that the tension components is not so clear, or actually it should not be 0. But in any case,
it seems that the nonlinear term is right.
No, it's absolutely correct because okay, I wanted to do it here. Okay, thanks. Here I write it here. So this one should be UE dot dV and then plus V dot Grenier. Is that okay? I'm sorry. So U nu is equal UE plus V. But okay, maybe that's just the way I like to write to be quick. Okay. All right. But of course you are right to with that. So with this, I mean, look at the difference. You do the which is what you want to do. Multiply by V.
So why this is boundary condition for V?
No. I mean, so whatever the boundary condition for Euler and Navier-Stokes give you that. That's all. I mean, it's not a new equation, right? In the sense that the boundary conditions inherited from Euler. That's all I say. Okay. All right. So you know for sure that u dot n is equal 0 because u dot n is equal to u nu dot n minus ue dot n. Okay, and this is equal to 0. But u dot tau is central components. So this is omega. You have n, and you have tau. Okay. So the tangential components you don't know. That's all I'm saying. Okay. And this is supposed to be very quick, in fact. So you do these computations. You multiply by v, integration by part. This u nu, integration by part of this is gone. Integration by part is this is not gone. Integration by part of this is gone. So you have that. So you get equal minus nu u nu dot gradient v. This one is still there. So integral of v dot gradient ue dot v. Okay. So I just multiply by v. In fact, I don't do anything except that I have the boundary terms, and the boundary term is plus nu, the boundary dn of u nu dot gradient of v. No, sorry, dot v. Yeah. Okay. Okay. And you realize that, okay, u nu is equal v plus ue. So this one you have a good term, v squared. Okay. And then the next term is just gradient ue, gradient v. So you can do Cauchy Schwarz. So we have this one over 2 plus nu over 2 gradient ue square. Okay. This one I do gradient ue L infinity VL2. Okay. So it left me with the boundary conditions. And the boundary conditions, I'm going to use a very quick lemma, which is a remark, is that nu dn u nu components. Okay. And if I hit the tau, then this one should just be nu vorticities cross n tau. Okay. Actually, this one is only true if u nu dot tau equals 0. In fact, yeah. But in any case, the boundary terms I get here is nu, the boundary terms, vorticities cross n tau, because v you have two components, ue and u nu. U nu is equal to 0, so you have ue. Okay, ue tau, and tau is supposed to be the tangential component. Okay, so these very simple calculations give me these inequalities. d over dt v squared. In fact, probably it's already clear from here. Maybe I can just do Grenier. I think everyone should know Grenier already, so just to save some time. I have the dt of v squared. Everyone is 1/2 is perfectly 1/2. Multiply by 2, you get here. So the Grenier is about give you sub in time L2. Okay. All right. Less than or equal to exponential of integral in times. But I'm going to just take the sub out. Infinity in t and x times t, probably big T, of of this kind. Nu, radiant integrating time, radiant UE. So this one is just the ground war. There's nothing fancy about that. Nu, integrating time, maybe absolute value, integral of vorticities. Okay, and UE. Probably with a dot. Okay, that's what I wanted to get. Very simple calculations to get. And now I want to make remark about this. Okay, so what was the problems? The problem is the implicit limit. You wanted to try to prove that the solution of Navier-Stokes converging to the solution of Euler in L2 norm. At least that seemed to be a very natural norm with the energy norm. You do a quick calculations, multiply by V, integration by part. The problem is that UE. The problem is that the solution of Euler, there's no guarantee that this one is 0, right? So it may be UE of tau should be no 0, because there are many examples of Euler solutions that, of course, the tangential components is non-zero. And simple calculations, then you use the ground wall, you get that. So this is what you get. All right? So this is okay. Remark: in the case no boundary, okay, implicit limit is trivial. Here, at least for smooth datum, we get U nu minus UE. So implicit limit is true. All right, up to the time constant of Euler, in fact, is go to 0, and is less than square root nu. Okay, so of course go to 0. So that's the first remark. Of course, maybe since I said implicit limit without a boundary is trivial, as I wrote, but I should be careful because maybe mentions for less regular problem. There are still open problems, in fact, and one of the sources that you can consult is this very nice work by Thierry Gallet, and also the recent work by Thierry and Sver. Okay, so you can look in there to get some appropriate references. But the problem is, in fact, open. In fact, I mean, completely open, in a sense. All right, but however, the case that I care is the case where initial datum is very smooth. So you can take a sufficiently smooth initial datum, at least for my lecture. Then it's trivial. Okay. The second point. The second point is that in the case the boundary is not empty, meaning that you have some boundary. You have some boundary, then you have to deal with that. Then you see that at least we have the implicit limit hold if only if, let's say, new vorticities go to 0 in some sense. Okay, go to 0 in some sense. Okay, so at least what I'm trying to say is that you need some kind of quantitative understanding of vorticities, right? So vorticities is, of course, by definition, is cross of nu. So it seemed that, sorry, it's on the boundary. So it seemed like the boundary vorticities is the, right? So the boundary vorticities is issue. So maybe let's put that in red. So the boundary vorticities is the main issues. Okay, the boundary vorticities. So you need to understand the vorticities, the vorticity on boundary. Okay. In fact, there are many works in the case with boundary, but maybe just to mention this kind of results, or this if this kind of conditional results, we often refer to just Kato conditional results. Let's say Kato conditional results. Oh, conditional results. Why not? Okay, this is of course by Kato, 86. And in fact, in the whole space, first result that I am aware of is actually Kato 72. But okay, it's just as simple as that. The Kato conditional results is in fact the implicit limit hold. You have UE, if only if a new integral in time, integral of, you have a distance to the boundary of order nu, and you knew dx dt go to 0, okay, which is of course the similar conditions, but okay, I'm not going to derive that for you. It's just to mention the literature out there. All right. So that's the remarks. Remark number 3. Actually, that's all remark for now. Okay. Do you have any questions on that? Yes, please.
What's an example in which Kato criteria holds?
For the nonlinear equations?
Yeah, it just
No.
So, no, I'm just saying, what's an example in which you can apply Kato criteria?
No, I mean, okay, that's a great question. The problem is completely open in a sense, in precise sense. So there's no examples, but okay, actually I give you examples here. I give examples, which is the third remark, maybe the third remark. Yeah, third remark. That's a good question. Here are examples. Maybe examples I give here. That's a great question. Yeah. So maybe let's put the remark number 3. Remark number 3, in fact, is that, in fact, we have this for analytic data. Okay, for analytic data. Okay. In fact, now we know that it's just locally analytic data is okay. Okay. Locally analytic data. We have this. We have a bounds on vorticities, and the bounds like this. The vorticities on the boundary, is bounded by nu t minus 1/2. Okay. For analytic data or locally analytic, meaning that you only need analyticities near the boundary. So you have your boundary, and you only need analyticity near the boundary, in the distance near the boundary. And if your datum is analytic, then you can bound vorticities. Okay, you can bound vorticities, and in particular with these vorticities, then Kato conditions and host, of course. And for the completeness, let me mention some previous work on this problem. Okay, so that board is naively as a student to try, and that's all you get. So let me give you references or the results on this problem. So it starts with the work, the classical work, very beautiful work by Sammartino and Kasflet. Actually, every time I write this, I remember told me that the previous one should be asymptotic. So I think it's about the same time. Okay, and what they do is for analytic data. In particular, you have that bounds for vorticities on the boundary. Okay. There's another beautiful work by Miyakawa, where he does for compactly supported. Data, and in particular, the data can be overlap, can be just as C4. I think it's just C4 in the interior. Okay, and by the way, all of these are in half space, but that's okay. This is the results in 14, and building up some analysis and approaches that I done with Emmanuel. I did something. I mean, we work on this with my former students, Tring. So let's just say we have the same last name, so N square. We essentially reproof this, but also for analytic datum. But in there, we really follow the approach that Miyakawa did with the vorticities formulations of these classical results, and Kukavisa, Wang, and Vico build up on what we did and able to treat the problem when you have datum is only locally analytic. So you only need analyticity boundary, and all of these are in half space. And then recently with Claude and my students, we treat the problem for any bounded domain. Okay. For any bounded domain, and you only need analyticities near the boundary. Okay. You only need analyticity near the boundary. All right. I wanted to write out the formulations that we use, and as an exercise of my course, hopefully by the end of today, you will be able to prove this within a few minutes, in fact. So let me give you the formulations, very quick formulations, because I thought it's beautiful to explain why vorticities, at least in the case of analyticities, vorticity is looking like that. Okay, just very quick, very quick. So this is in this work we use vorticities formulations. Okay, vorticity formulations is looking like this.
Sorry, when you say compactly supported, that's outside of the boundary.
Exactly. So yeah, that's a great question. The result of Miyakawa is that the datum of the vorticities here. So the result of Miyakawa is equal 0. So vorticity is equal 0 near the boundary. So inside is overlap. Okay, and this is the result of Miyakawa. Okay, and the results with all of this work, and the final one is with Bados and TT. We only need the initial datum to be analytic near the boundary. Okay. Okay. Near the boundary. And because the formulation is quite simple, so, at least to explain you very quickly, the vorticity is looking like that. In fact, maybe I only do in 2D for this for all of these results, only in 2D. But okay, one can extend it in 3D. But you can see. So for 2D, the problem, the equation is this. So you get a vorticities, right? You get a vorticity is equal. Then the equation for vorticities, which you have already seen, except now some terms I put on the left and some term I put on the right. In fact, that's all to it for this kind of analysis. And there's the boundary conditions because the problem. So at least you may have a feeling already that this problem is hard because there's something going on the boundary. Something has to do with vorticities. Okay. And the boundary conditions is this. So nu dn of vorticities, dn of vorticities. So the boundary conditions for vorticities is, well, let me just write that. W on the boundary is equal to okay, I have to derive it to know what it is. In fact, gradient n above a plus and inverse of u dot gradient omega. On the right hand side could be wrong. I can derive it very quickly for you, but my point is that in the case of analyticities, you could in fact put all the nonlinear on the right hand side, because somehow with the analyticities, the loss of one derivative can be handled, and so the problems is really somewhat reduced to the Stokes problem on the bounded domain. And for the Stokes problem, or at least for the heat equations, that the behavior that you get. Okay, I'm not going to give you the framework to treat this, because you will see that the framework that I developed with Emmanuel is a bit more involved, and so as a consequence, maybe as an exercise for you to try after this, if you can get it for analytics, for the case of analytics. Do you have any questions? Any questions?
Okay, Toan.
Yes, please, Claude.
Before you read,
Yes, please.
very naive, but
Please, yeah.
we even comment on the ground wall at the very top.
Yes, that's a mistake.
Well, you say that the vorticity against the tangent component has to be bounded. I should add it's enough that it has a good sign, which means being negative.
Yes.
Being negative means that the vorticity on the boundary will, the bad side being positive, means that the vorticity on the boundary is in the opposite direction than the natural flow on the along the boundary.
Exactly.
Which
Yeah.
means that it creates what people in field mechanics see is a detachment point.
Exactly. Yeah.
Which,
Right.
in some
Exactly.
sense, all what's on the right,
Right.
Before analyticity,
Exactly. Yeah.
is avoiding the detachment.
Right. You can play with the sign to see. Yeah. That's a great remark. Yeah, that's a great remark. Yeah.
And
Thanks,
the
Claude.
boundary analysis, boundary layer will be also in a case where no detachment.
Right, we'll see about that. Okay. Let me try to do it now. Just to mention that this boundary conditions, which is very easy to derive, but maybe I should move to the next sections. But just to mention this boundary conditions were now what I call Anderson's Miyakawa. Okay. Boundary conditions. Okay. It's a very nice boundary conditions that tell you, at least you see the localizations of vorticities on the boundary in the case of analyticity. Okay. So now that So maybe I should mention also, since for completeness, for the sober data. So the interest is we're doing for sober data. Okay, meaning that, so you see that for analytics data, you're allowed to put this convection term on the left hand side, on the right hand side, and treat that as perturbations. But it turned out that for sober data, things are not quite as that, and the problem is completely open. Okay, so completely open. Completely open. Completely open for the implicit limit, of course. Yeah. Okay. Because as vorticities may become large than expected. Because the vorticities on the boundary may become larger than expected. So you may expect that bounds on vorticities is the right one, which is only nu t to minus 1/2. But it's not that for sober data, these terms create a lot of problems. Okay? Okay? And you will see that it's going to be larger than expected. A boundary vorticities conjecture that it could become very large, it could become of order nu minus 1. But all of these are completely open. So let me try to tell you about boundary layer theory. Okay. Okay. You see that when the datums is sober left, because the convection is very large, so this will do something, or at least trying to understand what's going on at the boundary. Okay. And so this is the boundary layer theory, which is theory that by Prandtl. So the Prandtl in 1904 already, in fact, and he's saying this. Maybe let me just say the problems. Okay, let me just say the problems. So the problems. All right. Okay. So you see that the implicit limit problem. I mean, I did not sense many more names that doing the Kato conditions and doing examples. Yes, maybe now I remember. Yes, doing examples where you have the symmetries. Okay, for instance, Michele, you were asking earlier. So for me, it's always in general. When the datum is analytic, you can get Kato. But in the case of symmetries, there are also a lot of work by Helena and other people. It's very interesting. That justify the Kato conditions. Okay, but in the case without symmetries, as I wrote, then this is the state of the art. Okay, that's okay. So for the boundary layer theory or boundary layer problems, is that okay? Again, for smooth, I always care about smooth data. U0. Then this one is of course. Other one is only L2. U satisfies. So the solutions of Navier-Stokes, at least in a short time, satisfy. Let me be a bit more precise. Sub T 0 of U nu minus the Euler. But now remember that I will change this the norm, so L infinities, and this is 0 as nu go to 0. So this is the problems where, of course, where maybe I should where UE solve Euler equations, and PR solve what we call the Prandtl boundary layer equations. Okay. So let me be a bit more precise before I discuss these problems. Let me be a bit more precise now. So, but before I even say anything, the problems here is in L2s, and the problems in L infinities, you're supposed to see more structure. And how to okay, maybe let's just like that. Okay, then the Prandtl analysis. Okay, so this is the problems. I will discuss it, but first the Prandtl analysis is this. Propose that when you are near the boundary, actually maybe I should be even more precise. The boundary layer theory, and I'm going to just take R2 plus, which means that in the space y is positive only, or x and y is positive. Okay. All right, and the Prandtl analysis is like this. So now you are in 2D, and okay, and you write u nu as u1 nu tx and y over square root nu, and square root nu u2 tx y over square root nu. Okay, so you propose an ansatz for the behavior near the boundary. Okay, you propose an near for the, so you have an equation like this. So this is Navier-Stokes equations. The equation is dt u1 plus u dot gradient u1 plus dx p equal nu dy square dx square u1 dt u2. So this is, of course, this is the same Navier-Stokes equations. I just write it's in a bit more components wise. Okay. Okay. And now I plug this ansatz in, and I realize that dx is remain dx. However, dy is square root nu of d big Y. Okay, so it's very easy to see that this one remains. This dot, it remains because the dot is always, the dot is u1 dx plus u2 dy, and u1 is the same order dx. So maybe I should say here, no, it's already there. u1 is the same as u1, but u2 is actually square root nu of u2. So it's very quickly you see that on this equation remains, but here you have dx. Okay. And for u2, you have everyone multiplied by square root nu. dy becomes 1 over square root nu. And here, everyone's multiplied by square root nu. Okay? Just because of u2. It doesn't seem right. Ah, yes, did you remove this? Sorry. This one, so this is nu. You get divided by. Okay. in any case. All right, so you get the Brando equations. Okay. dt u1 u dot gradient view 1 dx equal dy square u1 dy of p equals 0. You have still have the divergent free conditions. Okay, so that's the equation. Brando saying that near the boundaries, all right, all the dx x is small comparing to dy, so you only keep the leading term, and this is the leading equation of Navier-Stokes. So the Brando equation is the leading equations of Navier-Stokes, and it has a lot of advantage because one thing already that pressure is a function of t and x. Okay, and because it's only a function of t and x, so it's really the pressure of Euler t and x on the boundary. Okay, so that's already advantage that there's no pressure in the Brando. The Brando not only balance between the viscous force and the convections, but also correct conditions. Okay, from Euler. So u1 at y equals 0 is still equal 0. However, u1 at y equal infinity is supposed to correct the value of Euler. Okay. Okay. So this is the boundary layer equations. Okay. So this is what we call the Brando analysis. And maybe a remark is that, again, this Brando analysis is okay, meaning that it's okay, it's valid. Again, for analytic data, this is of course the classical results by Sammartino Casplis. Okay. And there are some examples, of stability or validity of these problems, validity, stability in geometry. Okay, that's a nice work, very nice work by David Gerard, Masmoudi, and Miyakawa. Okay. This lecture, at least the first part, which is the part that I will try to present to you, is the work with Emmanuel. And we'll be able to construct examples where that fails. Okay, so we go counter examples. Counter example for u nu minus ue minus u Brando in L infinity norm has a lower bound. Okay, has nu go to 0. I will be more precise, but this is the examples. This is the at least we try to give. In fact, it's not just the results, but the what it reveals is more exciting, right? In the sense that they go into very rich, very complex behavior at the boundary. In fact, okay, everything is at the boundary. All right, but this is at least the introductions of what's going on. Okay. Any questions? Wait, no. I still have time, no? Cool. No, wait. I have until what? No, I have until 10:30. Christoph, you got me 50 minutes. 10:30. 10:30. I still have time, no?
Maybe you can write explicitly what is the worst nonlinear term in U gradient of U1. What is the really bad one, which makes the problem?
Yes, of course, I will. Yeah, of course, I will. No, I will. Yeah, of course, yes. Yes. No, this is just the introductions of what's going on. I'm going to do analysis now, but because of course analysis is very delicate. So if you get into that right away, then no one going to follow for sure. But at least this is okay. Yes, please. Yeah. Exactly. Yes. Exactly.
And so
It's a scalar equation. Yeah.
in terms of the system, we're just saying that there is a U2 such that.
No. It's a transport equation for U1. It's a transport diffusion equation for U1. But then there's U2, which is not local.
The equation for U1.
I'm sorry.
But there is U2
Yes.
with the
Yeah.
which
Yeah.
was not from this guy.
What you mean, Claude? Sorry. Sorry. No, sorry. Okay. So of course this one. Okay, this one is U. Maybe let me be precise here. This is U1 dx. Okay, so the big one, yeah, big one. Thank you, Claude. So you have these equations. So it's the equation for what? And of course, you could write an equation just only in U1, but then U2 is yes, I see what you mean. I want U2 is also equal 0 on the boundary. I see what you mean. So you want U2, okay? So U2, solve it, right? 0 to y dx d1.
And then the dx, which is the vorticity on the boundary, which is the source of the problem.
Yeah,
dx
of course.
Is all still the vorticity of the boundary.
Right, of course, yes. Yeah, thank you. Okay, so this is at least the picture that you see for these kind of problems. All right. So with the boundary, you see there's some ansatz, or at least something going on the boundary, which may be more clear. Trying to naively prove the boundary layer problem. Okay, just like what I did here for implicit limit, and we fail, but only cases that are correct. Okay. Have question? Yes, please.
If instead of the half space you have like a disk, you should change the answers, etc. Like
Yes, exactly. Yeah.
someone did it, or
You mean the boundary layer equations for? I don't know if anyone did that, yeah, but yes, maybe some effect of curvatures coming on. Yeah. But actually, the boundary layer equation is almost the same. In fact, it should be almost the same. Yeah, it's almost the same because the curvatures seem to come in the next order. All right. A great question. Okay, of course, I haven't really done anything in terms of understanding the boundary layers. I only tell you that's the answer. Okay, and so of course then you examples we're going to work with is that, so the examples, or at least the examples are the case of focus. Maybe let's just say the case of focus. How about that? Because the rest is just only this case of focus. It's the case where U random is exactly a function of t, a shear flow. Okay, this is type of shear flow. It's shear flow where dtu equal dy square u. Okay, and then ut equals 0 is equals u0, which is only a function of y. And of course, it satisfies whatever the conditions you have. Maybe I write. No, wait. That's it. Okay, and of course, u at y equals 0 is equal 0, and u at y equal infinity is equal 1. Okay, this is really the case that we're looking at. To write this as approximate, okay? Because okay, fine. Save sometimes. Okay. Anyway, so you get this, right? And then you see that the okay. Then what you wanted to do? You wanted to say that, okay, so the boundary layer problems, right? Or the whole boundary layer problem is to prove the stability or to understand the stability of U random, okay? To understand this. Okay, so you have an ansatz, at least that's what we when you're subtracting the ansatz, you get the small thing, okay? And then you get that equations. So of course the equations comes, okay? All right, it's maybe I write in the in the style that no, okay, fine. So this is u dx, okay, of v. No, maybe I should be precise. So v is u nu, which is Navier-Stokes solutions, subtracting the ansatz you have. By the way, in this case, Euler is just 0 and 1. So because of this, so Euler. Yeah, please.
I don't understand why at y infinity does not match Euler solution.
No, it should be 1. Yeah, that's what I mean. The Euler should be 1. Yeah. Euler should be 1. Yeah, sorry.
Okay.
In fact, there's the way I define the way I divide the yeah, okay, anyway, the Brandon solutions are supposed to be subtracting the endpoints of Euler, but okay, this one should be the okay, if you want. Yeah. So this one is this is why I wanted to write the U app. Okay, it's the Euler plus the Brandon if you want. Okay. All right. Okay. And in fact, even that ansatz UBR over there, it should be plus Brandon. The value on the boundary.
You're right. So
Okay.
it's 0 if it's.
I'm sorry.
If you take Euler plus Brandt at y infinity, it's 0 since Euler. No, it's 2.
No. Just this. So just this and this. Okay. This is the total of Euler plus Brandon. This is the total. If you want Euler is this, the Brandon. So just the definition. Brandon layer is supposed to be just U minus 1. Okay. Okay. Because the Brandon layer correct the value of non-zero of Euler on the boundary and decaying to infinity. Okay, to be really precise. So including, but okay. So you had a V is the difference of u Navier-Stokes to Prandtl equations. Okay, you got an equations. So the equations look like this. You have okay. So this is the equations. This is the exact equations. And because of the Prandtl corrector, you get v dot v on the boundary is equal to 0, which is in this case just half space. Okay, equal to 0. Okay. You get that equations. Oh, you're right. I'm missing the nonlinear term. So maybe put nonlinear term on the right. In a way, the whole story, if you realize, is that when to put the stuff on the right or on the left, in fact. Okay. And we learn from. So we are allowed to put. I mean, for the analytics trees, you can put everything on the left or on the right, but in fact, for Sobol F, or at least in this Andiats, this one is very large, so you cannot put it on the right, so you have to move and understand this operator, in fact. This is the usual story as we do with these. Okay, so you see that for this one, at least now we have established ourselves how to do an energy estimate for Navier-Stokes. You see right away the problems. So again, do you see the problems already? Huh? Okay. You have questions? Yeah, it's okay. I mean, I write out the equation for difference, and I wanted to bounce the difference. Okay. This is the usual story. And the energy estimates, of course, without even writing it, we know that it fails. Or at least it doesn't give you anything. Maybe it's already clear for you. Now you have the correct boundary conditions. If it's okay for you, I can just write down very quickly what's going on. Multiply by v, integration by part, you get this. So of course, the energy estimate is useless in the sense that, so this one is okay, this one is okay, so the only thing left is this guy, is integral of v2 with the signs dot v. Okay, wait, sorry, dot v meaning just v1. And I don't think you can do anything here. This one is dy u approximate very much v now 2. Okay, so the energy estimate only give you the v in L2 is bounded by exponential of dy u approximate infinity t of v in this datum. Okay. Yes.
Is u up? No.
V. Sorry. Okay. V u up, yeah. Okay, so which means that we have to really understand the linearized operator, right? I mean, okay, but I don't. Okay, let me say this. Here's all problems, right? Because remember that u abs is a function of y over square root nu. So this one, dy of u approximate in infinity is of order nu minus 1/2. Okay, so in a way, the estimates that I gave here, is really tell you that the semigroup of the linearized operator, okay, I did not write down anything explicit here, but it tells you that the semigroup is very large, right? It's impossible to do anything. It's exponential of C0 T over square root nu. Okay, let me be precise. So let's say this one is multiplied by C0 nu minus 1/2. So the semigroup is very large. Okay, L2 to L2. Okay, so you already see that this is the problems. These are the problems. Okay. And the convection is very large, so we have to understand this. And energy estimate alone doesn't tell you that this one remains close. Except you take the initial term is like super exponentially small, then you can beat this. But otherwise, it's very large. It's useless. It's useless in the sense. Okay. And so one has to understand the linearized problems. So maybe this is linearized problems. No problems. Okay, which means that the linear equations. Okay, so the linearized means that okay, let's go step to cancel the linear. We got the linearized problem. Okay, and it's this is actually an idea already in the classical paper by Grenier that because there are some scalings that you have to look. Okay, pretending that this box is a sine of square root nu. Okay, and the idea is to introducing the hyperbolic scaling. Okay, to capture what's going on for the linearized problem. The problem already, right? Because the linearized, because the semigroup is very large, it's grow like exponential. It is useless, and we have to add a bit more on the linear problems. Okay, linear problems. So you do the scaling. You get scale t, x, and y. You scale right in this box, okay? So you scale everyone by square root nu. Okay? Scale everyone by the square root nu. And see. And you see that the equations, in fact, for the Euler equations, this scaling is invariant. Huh? What? Yes, exactly. This is what I mean by hyperbolic scaling. Oh, yeah. So I'm going to scale for Euler equations. I scale because the Euler equations is invariant with the scaling, so it doesn't change, but it only changes here. So the equations are the equations. So the linearized, I mean the same for nonlinear, in fact, but okay. Linearized equations. In fact, if you okay, I don't know. Okay, I'm going to just write in the vorticities form to be quick. In vorticity form. Okay, so vorticities here is at omega. Well, the scaling doesn't do anything except it's only scale the viscosities, nu by square root nu. So maybe I just say word here that Navier-Stokes remain the same. With viscosities, nu changed by square root nu, because that's the only thing changed here. Okay, and then I get a Navier-Stokes equation, but now I look at the vorticity form. So you have seen this. So dt plus u, but now it's only functions of square root nu ty dx vorticities. I define plus u plus dy square of u, a function of square root nu t and y. Okay, so I change small y to big y of v2. Okay, of v2. So this is of v2. All right, of v2 equal square root nu Laplacian of w. Okay, and of course v1, here's the nonlinear remainder. And it's convenient with vorticities to write in terms of stream functions. Vorticities is the Laplacian of the green function, of the stream functions. And so V1 is just, at least the way I do, is dy of phi, and V2 is minus dx of phi. Okay, so I'm going to just change these equations. I'm going to do another change. Okay, so at least these are the equations. And okay, I'm going to do another change. In fact, maybe it's already here that that you see something going on at t already of order square root nu. Okay, so something already happened at t very small, and so I'm going to drop the dependence of u in time, and so even the maybe the first okay, so these are the equations. And now I'm going to drop the dependent in time because, at least that what one has to understand first. So we can further approximate u square root nu t y to be u of y only. Okay, this is the CF flow that I'm going to take. Okay, and the fact that it's dependent on time, there has to be some other arguments to treat that. But now I wanted to understand the linearized problems. Let me just rewrite it: dt plus u dx. Exactly the kind of CF flow you have seen many times in this conference. Dx of phi equal square root nu Laplacian of omega. Okay, and the boundary conditions. Now, okay, so omega is the Laplacian of phi, and the boundary conditions I'm going to take is, just the no slip conditions. Equals 0. Equals 0. Okay, so this is the linearized problem. Okay, just to understand that. Okay, because the convection term is very large. As this is the only issue, in fact, large convection term, but discuss all the problems as usual.
Sorry. If you take the approximation with why do you don't take the viscosity go to 0?
With
here you take one approximation who says that it's like viscosity go to 0 in this case.
Yes.
Yes, and why do you don't take the linear Z problem?
No. The first step is I want to understand the linearized problem near a steady state shear flow. That's what I'm saying.
Okay.
That's it. Okay, because This is how we should do. When the problem is harder, you reduce the problems until you can understand. Even the shear flow, you will see that even the shear flow is already a lot of things to be understood. Okay, and I will tell what we have been understand so far. All right, and so you get these equations, and for these problems, see that. So I'm going to do again. This is a natural thing to, as a first step to do, is to look at mode by mode for this linearized problem. Okay. So what we're going to do is to do in X of this sense, and we're going to take Laplace transforms. Transform in T, and you get these equations. You get lambda T, or lambda plus. So lambda is the Laplace transform variable for T, and alpha is the Fourier transform in X. You get ik, I alpha u. Okay, W. And actually, I'm going to write W in terms of Laplacians. So it's Laplacian alpha of phi u double prime equals square root nu Laplacian alpha square phi, where just for convenience, Laplacian alpha is square minus alpha square. So alpha is the variable in X. Fourier variable in X, and yes, thank you. All right, and in fact, it turned out convenience to take lambda to be minus I alpha C, in fact, because you could divide everyone by I alpha, where C is a complex number. C is complex. Okay. Then you get an equations as follow. You get U minus C Laplacian alpha minus, so I alpha I just divide it out, equal epsilons square phi. Okay, where epsilons for convenience is square root nu I alpha. Okay, so you think of that epsilon is very small. So the boundary conditions is I alpha phi at y equals 0 phi prime at y equals 0 and phi at y equals infinity is 0. Okay, so this is the famous, this is the classical Sommerfeld equations. Okay, Sommerfeld equations. Is it for order ODE? If you're not already clear. Oh, equations. Okay, is it for other problems? Maybe problems. Okay, and maybe I can just say right here that this is I can just say right here that okay, first of all, it's a fourth order, so it's clear. Okay. Second of all, if phi, alpha, and C is a solutions to the isomorphism. Then you see that V, which is the gradient verb of exponential of I alpha x minus ct Vy. Okay, that's V. Is the solutions is mod solutions to the linearized Navier-Stokes. Okay. By mod solutions. And if imaginary part of imaginary part of C is positive, then V is growing. Okay, V is growing. Okay, oh, exponentially growing, exponentially in time. Namely, V is like exponential of alpha imaginary part of C t. Okay. All right. And you see that this one, and at epsilon equals 0, we get Rayleigh equations. Rayleigh equations. Let me just write down for the sake of completeness. It's the second order ODE, which probably you've seen from last talk of Maria. What is about the conditions? Yeah, so you have this, just the conditions. Okay. By the way, in the case of alpha equals 0, the equation reduces to just the heat equations. So alpha is always non-zero, in fact. So you only have the condition on phi. Okay, and again phi at y. Okay, so at least from this point of view, the isomorphism of Rayleigh. Okay, and this issues, in fact, lead to all issues. Okay. All right. Right. You have any questions? So far it's just derivations of some. So this is the problems, and it reduces it to that. Of course, this is of course the singular perturbation problems, because epsilon is in a higher derivative, and by itself you need boundary layers. Okay. Yes. Okay. So what we do, we really have to do the kind of Brando analysis, adding the boundary layers to treat these fourth order ODEs. Okay.
Just a question.
Yes, please, please.
How many boundary conditions do you need exactly? So you hold 3, but we expect 4, right?
4, in fact, the second derivative of phi at infinity is on equal 0.
The second derivative of phi at infinity.
Yeah, because of the. Yes, please, Matthew. Yes, please.
Assume that U is a constant in time. If you plug this association in the integration, you have that like dy squared u equals 0.
Exactly.
So what is the motivation for taking
Well,
The approximation then you should have used
no, I mean, what I should say is that this is a first problem to understand. Once you understand these problems, then that problems is exactly, you have some error term. So I'm going to write the error term, but I'm going to erase it right away. So you see that the error term is what is this u square root nu t minus u at no time, right? Times the x of omega plus the other term. But we're going to treat that this one is actually of order square root nu, in fact. You know? So we're going to have to iterate more and more. But as a first step, just to understand a linearized problem, we understand that. Okay? Maybe in a few minutes, okay, I was planning to do the singular perturbation analysis for you, at least in the easy case. And the plan is to give you the new approach that we developed to treat the nonlinear problems. But we'll see how it goes. So maybe let me just summarize. Sorry, not summarize. Let me just leave. Let me just say like this. I have a few minutes to say. So let me just say like this. So you now optimal E, and the problem has become increasingly delicate. But you see that there are two cases now, because one is the shear flow is spectrally unstable to Euler, or of course it's Rayleigh. Okay, I'm sorry. But, yeah, it's okay, but please ask. Yeah. So, at least more or less to summarize, is that okay? You see some ansatz, the boundary layer ansatz, and naively you subtract the ansatz and trying to prove the stability. If you do energy estimate, it's lost because there's some growth. Then it reduces to understand, or what you really have to understand is to understand the semigroup of the linearized problem. Okay, in order to do whatever analysis that you can. Then, if you do reduce to the spectral problems or the linearized problems, I even reduce further to resolving equations, taking Fourier and Laplace transform. You get some ODEs, and from that ODEs, it seems like perturbations of Rayleigh when epsilon is equal to 0. So you see immediately two way already. If the shear flow is unstable to Euler, then we're able to construct. To Navier-Stokes. Okay. And the plan was to tell you that even this one, and then we're going to prove nonlinearly. Namely, exactly with this ansatz, we're going to prove that u nu minus u approximate in subnorm is of order 1. Okay, so this is at least the plan that I'm going to do in the afternoons. And 2 is in the case when the shear flows uy is spectrally stable to Euler. The picture you have in mind, it should be the pictures you have in mind. It should be that the unstable one. So the shear flow should look like have an inflection point, and the one, the shear flow has no inflection point. There's monotones. So this is the picture of U, the picture of Uy, in fact. Okay. Then in this case, in fact, linearly, still a growing mode to Navier-Stokes. Okay. So in all cases, we're going to prove that at least for this one, linearly, we have some nonlinear results also, but linearly is already unstable. So this is the results with Django. Wait, Emmanuel. And I'm going to focus on the first one because in the first one we're going to develop some analysis that be able to prove the nonlinear results. Maybe that's finished for the morning. Yeah. Thank you.